What if I told you that you don't need numbers, you don't need booleans, and you don't even need data structures to build computation? Actually, all you need is functions. With nothing but anonymous functions, we can encode arithmetic and logic from scratch. I know this sounds counterintuitive. What are functions acting on then? Well, if you recall, in the previous two videos, we said that functions in Lambda Calculus can take other functions and even the function itself as an input. In other words, we will consider functions who act on functions. The only atomic entity we will consider is that of the function. Today, we will build true and false, so the Boolean values, and or and not, so the operators which act on Boolean values, natural numbers, and addition and multiplication, as well as the successor function, by the way, all using pure Lambda calculus. So we will build all of these notions and operators just using functions. We will start by encoding booleans as just functions. This is called the church encoding of booleans. The key idea is the following. Essentially, when we think of a boolean intuitively, we think of a binary value which represents a binary crisp truth-falsity dichotomy. That is a 0 or 1. From a philosophical point of view, this dichotomy can be mapped and has been mapped to various other dichotomies which naturally arise. In the famous poem by the pre-Socratic philosopher Parmenides, named On Nature, which according to some has been one of the first works in philosophy advocating a strict monism, the following is said about the binary distinction that men have adopted regarding the world. Men have determined in their minds to name two principles, but one of these they ought not to name, and in so doing they have erred. They distinguish them as antithetic in character, and give them each character and attributes distinct from those of the other. On the one hand, there is the ethereal flame of fire, fine, rarefied, everything identical with itself, and not identical with its opposite. And on the other hand, opposed to the first, is the second principle, flameless darkness, dense and heavy in character. Of these two principles, I declare to thee every arrangement as it appears to men, so that no knowledge among mortals may surpass thine. But since all things are called light and darkness, and the peculiar properties of these are predicated of one thing and another, everything is at the same time full of light and of obscure darkness, of both equally, since neither has anything in common with the other. Let us discard the philosophical ideas advanced by Parmenides for now, and just focus on how the notion of true and false has been always metaphorically mapped and represented through semiotic tools borrowed from the physical world, such as light and darkness, left and right, sun and moon, and so on. In essence, in order to encode true and false through lambda functions, we will do exact same thing. Map this epistemological dichotomy onto a physical dichotomy. So essentially a boolean is a function that chooses between two things, a left input or a right input. So we encode true as a function that given two arguments selects the first one, i.e. the left one, and false as a function that given two arguments, that here we name t and f, selects the second one, that is the right one. Now that booleans choose between values, we can define logic, and in particular logical operators that operate on boolean values. The first logical operator we will define is the not operator. Ideally, the not operator should flip a boolean value, that is, turn 0 to 1 and 1 to 0. Our goal is to define a function that does exactly that. That is, when we pass true, considered as a function as shown before, it will give us false, and vice versa. The function that achieves this goal is the following one. It is defined as a function that given an input b, it maps b to the following expression, b false true. In order to see that this is exactly the function we want, for a representation of the operator not, let us verify that it actually flips true and false as expected. We will do this via a substitution of the expression for true and false in place of b. Formally, to prove these results, we use a technique called beta reduction. We will see more about this in the following videos. We can define AND with the following rule. If the first input is true, then we want to return the second input. And if the first one is false, we're going to return false. And the lambda expression that will achieve this rule that we define just with the means of language is the following. As an exercise, the viewer can try to compute AND x and y for inputs x and y ranging over the values true and false. So essentially 4 possible combinations, and check that such an expression actually satisfies the AND truth table. So to define OR, the idea we will use is very similar. Essentially we say if the first input is true, then just return true. Otherwise, we're going to return the second input. And the expression that achieves this is the following. The expressions we presented for AND and OR are not the only way we can encode AND and OR in Lambda Calculus. The following is an equivalent form for AND. And this is an equivalent expression for the OR operator. Putting them together, these two form two equivalent encodings for the AND and OR operators in the Lambda Calculus. We will now encode numbers using the Lambda Calculus. This encoding is called church numerals. Now, the core idea is representing a number n as an application, an iterative application of a function n times. So this is how we're gonna encode the concept of quantity as a function. And so the number n is just a lambda function of 2 inputs, f, the function we want to iteratively reapply, and another input x, and essentially the number is just this function f applied n times to x. So let's see a couple of examples. We're gonna see how to write as a function 0, 1, and 2. So 0 is just a function applied 0 times, which is just, in this case, x. Whereas 1 is a function applied 1 time to x, so it is f of x. And 2, well, 2 is just f of x, and so on. So the rest, of course, is not needed to see how to represent the rest, because it's pretty obvious. I mean, it's just an extension of these. Having now defined numbers, it is now reasonable to define operators between them. And the first operation that we will define is that of the successor, which is an operation defined in the Peano axioms for the natural numbers. The successor function is essentially given a natural number, get the next one, which in terms of the operation of addition can be seen as just addition of 1 to the number. So the successor function is just the following expression in lambda terms. And the idea is that of given a number, the successor of n is just saying apply, let's call the number n, then apply a function f n times, and then apply one more f. As an example, the successor of 2 is just another application after the application of 2 times f. So it's going to be f of f of f of x. We're now ready to define addition, which in an axiomatic sense, it's technically an iterated application of the successor operator. To add 2 numbers m and n, the expression in lambda terms is the following. And essentially what we do is we first apply f, the function that, the given function we're going to reapply multiple times, n times, then apply the same function m times, and in total we're going to apply the function m plus n times. Whereas for the multiplication, the idea is similar, but this time, given 2 numbers m and n, m times n as a church numeral is going to be given by, as this formula represents, first we're going to take f and apply it n times. Then we're going to apply nf, which is f applied n times, m times. This yields an application of f m times n times. As an example, let us consider 2 times 3. It just maps the church numeral 2 and the church numeral 3 to the church numeral 2 times 3, 6. That is the application of the function f 3 times, 2 times, which is essentially f applied 6 times. So in the end, in this video, we define all essential data types and operations between them as functions in the Lambda calculus. In a way, it is as if we express all nouns of a language, as well as the verbs that link them, as a verb. In the next video, we will see the beta reduction and the alpha conversion, which are the two fundamental rewriting operations of the Lambda calculus. And as we also said in this video, we use these things throughout this video without going into too much detail. So in the next video, we're gonna explore it a little bit more carefully. With this said, I thank you for viewing this video.